All right, so I'm going to try to reproduce this lunchtime discussion about ABC, or approximate Bayesian computation, and the intuition thereof. The idea is that we want to simulate from a bivariate distribution, and we'll call our two random variables theta and x. And we want to suppose that the joint distribution of theta and x will be defined as follows. First of all, we're going to define a marginal distribution for theta, which I'll call pi of theta. And then given a draw from pi of theta, I'm going to define a conditional distribution of x given theta. And of course, the product of the marginal for theta times the conditional for x given theta is the joint distribution. And it's very easy to simulate from a computer using just that method. In other words, simulate from pi, and then taking that theta, we can simulate from the conditional for x given that theta. And what we obtain is then a sequence of bivariate draws from the computer. Theta 1, x1, theta 2, x2, theta 3, x3, and so on. And if you look at this sequence of bivariate draws and ask the question such as, what is the marginal distribution of thetas from this sequence? Well, it's obvious. The marginal distribution of theta is simply pi. However, suppose that we believe that x has some fixed value because it's the outcome of an experiment, and we will label the value of x, x obs. So our data tell us that x is equal to x obs. And now we look back at the original sequence of bivariate draws that we obtained, and we cross out any of them for whom x is not equal to x obs. So we look at the first one, and maybe this one is equal to x obs, and so we keep it. The second one, it's not equal to x obs, and so we get rid of it. The third one is not equal to x obs, and so on. And so we're left with a subsequence of draws, bivariate draws, for which the x values are equal to x obs, which is the value that we observe from our data set. Now you ask, what is the marginal distribution of theta from the subsequence? And we know how to do that because it's merely the conditional distribution of this bivariate distribution given that x is equal to x obs. And so we know how to do that. So the distribution of theta given that x is equal to x obs is the joint distribution. So we have pi theta, and here we want the probability, or the distribution of x given that we know theta and that we know that x is equal to x obs. We're going to divide that by the probability that x is equal to x obs. Well, so what is this? In the Bayesian context, of course, I didn't choose these variable labels by accident. In the Bayesian context, theta is often the parameter, and this would be called the prior distribution. The conditional distribution of x given the data and the value of the parameter would be called the likelihood. And we know that the prior times the likelihood is proportional to the posterior distribution. And so if we do this scheme from the computer and throw out anything for which x is not equal to the observed data, then we're left with a distribution of theta, or a sample of theta from the posterior distribution. And that's often what we want. We could call this an exact Bayesian computation, or EBC if you want. That's not a thing, but it's in contrast to ABC, which is approximate Bayesian computation. What is that? Approximate Bayesian computation basically takes this idea and simply replaces all the equals by approximations. And so ABC means that we simply have pi theta, the probability distribution of x conditional on x on theta, and x is approximately equal to x obs, divided by the probability that x is approximately equal to x obs. Now, of course, there are some details that need to be hammered out here. What do we mean by x approximately equal to x obs? Generally, that means we have to define some sense of distance, and maybe we want to say that the distance between the true x, or x obs, and the x that we've sampled is less than some epsilon. Anyway, there's details to be worked out, but this is the general intuition. If this is an exact sample from the posterior, then by replacing equals with approximations, we get an approximate Bayesian computation.